Hello friends, I'm Dr. Gaurav. In this video, I will discuss about enthalpy in thermodynamics. In the analysis of certain types of processes of control volumes, particularly in power generation and refrigeration, we frequently encounter the combination of properties U plus PV, where small u is the internal energy per unit mass and PV is the flow energy or flow work per unit mass, where P is pressure and small v is the specific volume. You can see the figure in which we are having a control volume or open system and fluid is flowing in this system and also exit the system. So there will be a internal energy associated with the fluid as well as the flow energy associated with the fluid. So the term U plus PV is generally encountered in this type of cases. The widespread use of property enthalpy is due to Professor Richard Mollier, and he referred to the group U plus PV as heat content. It is defined as total heat content of a substance. In 1930, the term U plus PV was replaced by the term enthalpy, which is taken from Greek word enthalpion, which means to heat. So the term U plus PV is represented by H, where small h represent specific enthalpy and capital H represent total enthalpy, where capital U represent internal energy, P represent pressure, capital V represent volume, small u represent internal energy per unit mass, P represent pressure, small v represents specific volume, that is volume per unit mass. Enthalpy is an extensive property, but specific enthalpy, that is small h, is enthalpy per unit mass and it is specific property. Isenthalpic process means enthalpy is constant, that is H1 is equal to H2, and this is in case of throttling process. It is one of the example of isenthalpic process. We know that H is equal to U plus PV. For small change, we can say dH is equal to du plus P dV plus V dP. For constant pressure process, the term V dP will be 0 as change in pressure is 0. So we will get dH is equal to du plus P dV. From first law of thermodynamics, we can say delta Q minus delta W is equal to du, or we can say delta Q is equal to du plus delta W. We can replace this delta W with P dV because W represent work. So we get delta Q is equal to du plus P dV, where Q represent heat. So we get the second equation. Therefore, for constant pressure process, as we compare equation 1 and 2, that we can say change in heat is equal to change in enthalpy, that is Q12. 12 is the process from initial state 1 to 2. We can say H1 minus H2, or small q is equal to small h1 minus small h2 for the process 1 2. Constant pressure process is also known as isobaric process. So change in heat is equal to change in enthalpy, or we can say heat transfer during a process is equal to change in enthalpy. In general, internal energy is a function of temperature and volume, and enthalpy is a function of temperature and pressure. We know that for an ideal gas, PV is equal to RGT, where RG is the gas constant and T is the temperature. We also know that U is a function of T for an ideal gas, and as H is equal to U plus PV, as U is a function of T, and we can replace this PV with RGT. So what we have, or we got, H is a function of temperature only for an ideal gas, same as that of internal energy. We get this relation from this equation. So we can say enthalpy of an ideal gas is a function of temperature only, just like internal energy, but this is valid only for an ideal gas. Now we know that specific heat at constant volume and pressure for general material, we can write down Cv is equal to partial differentiation of U with respect to temperature, keeping the volume constant. As I have already tell you that U is a function of temperature and volume, so this Cv will be also a function of temperature and volume. And we can also write down Cp, specific heat at constant pressure, equal to partial differentiation of enthalpy with respect to temperature, keeping pressure constant. As I have already told you that H is a function of temperature and pressure, so we can write down here Cp as a function of temperature and pressure. But for ideal gas, internal energy and enthalpy is a function of temperature only. So we can write down Cv is equal to total differentiation of internal energy with respect to temperature. As U is a function of temperature only, so for ideal gas, Cv is also a function of temperature only. Similarly, we can write down for Cp, as for ideal gas, H is a function of temperature only, so we can replace this partial derivation with respect to temperature with total derivative. So we have Cp equal to total derivative of enthalpy with respect to temperature. As enthalpy is a function of temperature only for ideal gas, so Cp will be also a function of temperature only for an ideal gas. From above relation, we can write for an ideal gas, change in enthalpy is equal to Cp dt, or dH represents small change. Total change can be represented as uppercase delta H is equal to Cp uppercase delta T, that is total change in temperature. Or we can say uppercase delta into H, where capital H represent enthalpy, and small h represents specific enthalpy, is equal to mass into specific heat at constant pressure into uppercase delta T. So this equation is again valid only for ideal gas. For ideal gas going through isothermal process, that is temperature constant, then the change in enthalpy will be 0. It is also valid for internal energy. For isothermal process, in case of ideal gas, change in internal energy is also 0. We know that H is equal to U plus PV, or we can say U plus RGT, as we can replace PV with RGT. So we have replaced here PV with RGT. So we can say small change in enthalpy is equal to small change in internal energy plus Rg into small change in temperature. Now we can write down here, or we can write down du as Cv dt. Keep taking dt common, we get Cv plus Rg whole multiply with dt. Now if we compare equation 3 and 4, we get a new relation, that is Cp minus Cv is equal to Rg. That means this relation is also valid only for ideal gas. Thanks. Any questions you can write to me gaurav.citm@gmail.com.